So welcome back, everybody. And obviously you had a great weekend. Now, I wanted to give you some messages in the beginning and also guide a little bit the reading and the kind of videos you can watch, and also a little bit about the plans for the lab sessions. So today we are going to try to wrap up this discussion about resampling methods and the bias variance trade-off, which we started last week. And we are going in particular to look at a method which at the end requires less CPU cycles than the bootstrap method. And this is the kind of method which is widely used. It's called cross-validation. And essentially it's the one most of you are going to implement. And it strikes a kind of compromise between a bootstrap resampling, where you typically would deal with all the data points and redo this many times, with just redoing this some few times. And there is always a little bit of this trial and error when you use the cross-validation. So the results may change according to how many times you do the cross-validation. And we are coming back to that. Now, essentially also for project number 1, you can choose whether you want to write your own program for it, or whether you want to use the full functionality of scikit-learn, which we normally recommend, because that saves you a lot of CPU time and also own time. Now, coming back to some of the videos, the videos which you see here, some of them actually pretty good. This is Stat Quest. And I don't know if you have been looking at them. I know that some of you have. And they are at some point also pretty funny. And they give I'd say a pretty good pedagogical overview of what is going to what happens with the different methods. So after the resampling techniques, we are going to jump into our first classification method. So till now, we've been fitting functions, but one of the big applications of machine learning is actually on classification. And this could be true, false, yes, no, etc., etc. So you could have cases where you are going to do this and this with a certain probability, and then you would have classification whether yes or no. There is a famous data set, there are actually many famous data sets which have been used for pedagogical purposes, but also people have written papers on them. One is a credit card data set where they look at whether you default or not on your credit card debt. And then clearly the output is just yes or no, which is normally encoded as ones and zeros. So these are typical problems which we are going to encounter. And we obviously have to look at classification problems as well. This is a type of problems which we will also discuss in more depth in project number 2, when we are going to encode our neural network. Then, when we come to logistic regression, there are also quite some good videos. Now, a textbook which we have been referring to, which is not the main textbook, is the one by Hasty et al., which is called Elements of Statistical Learning, which contains a pretty good discussion on this, but Rashka has also a discussion of that linked with gradient optimization. And this is a case, like in Lasso, where you have to solve it numerically. And you will see quickly why this is the case. By the way, coming back to Lasso, I have deliberately not shown you examples of how to encode Lasso with gradient descent. And I'm leaving that as a small challenge to you guys. But during the lab sessions, I can point to you where you will find code examples. There are actually code examples in the lecture notes folder on GitHub. But we have been a little bit, how to say, I wouldn't say nasty, but we actually want you to think how you would encode it. Because this is the first method, Lasso, where you cannot find an analytical solution. And logistic regression is another one. And that's the normal case. And when we come to neural networks, using gradient descent method is the standard. Concerning the lab sessions, we also wanted to discuss the structure of the report and discuss a little bit about the abstract in the introduction. And probably you have already taken a look if you go down to the exercises. These exercises, week 39, give you some hints and advice on how to use, let's say, Overleaf. There is a template for a report if you haven't written a report before. And then also on how we would like you to structure the GitHub site and the how do you create a document. Many of you have already done that. Adding good figures. These are things we are more than happy to discuss with you at the lab. And clearly you will also continue to work on the programming in the project. But this is a kind of guidance on how to set up the report. And we are obviously hoping to give you feedback as soon as possible, because I know that quite many of you have not written a scientific report. So this is more to get you started. And then next week, there is no weekly exercise, because then we're just focusing on the project. So you can see here also on how we would like you to make the code available and presentable, etc., and how we reference. So take a look at all these small technicalities if you have not done that before. If you're pretty familiar with it, I mean, then you can just proceed and start doing things immediately. Any questions to the exercises this week? So there's also a video which we recorded last year about writing reports. And if you feel for it, take a look at it. We also discussed there how to use ChatGPT, but that's also one of the things, or any of these similar softwares like DeepSeek, etc. So feel free to discuss with us in case you are in doubt, okay? But as I've said, this is something which we recommend using. And it's an extremely valuable tool if you're writing code to get inspiration, but also to find bugs in your code. If you're using, for instance, Google Colab has a pretty good AI suggestion setup. So if you have bugs in your code and it gives you error messages, it has always some suggestions on how to fix them, because sometimes it can take time to find the error. And especially when you're using Python libraries, because it can actually take a lot of time to find out what is going wrong with your own usage of that specific library. Okay, any questions? So let me remind you quick. So I'm going to use the first part of the lecture to remind you a little bit about what we did last week with the bootstrap bias variance. And then we are going to present the cross-validation method, which is also pretty simple conceptually. And it's also pretty simple to implement. But there, I mean, we normally recommend to use the ready-made functions which you find in scikit-learn. So resampling methods, they're actually indispensable tools in statistical analysis. So what they normally do is they involve repeatedly drawing samples from a training set and refitting a model of interest on each sample in order to obtain additional information about the fitted model. This is typically like getting a better estimate of the standard deviation. So let me quickly remind you of a typical situation which you will encounter when you use these methods. So let me bring back the whiteboard. So a very typical situation when we are calculating, let's say, the mean squared error. So the mean squared error is a typical function which we use to assess the quality of a model. Now, when you've done the training and everything, you are obviously going to test that, the model and the predictions your model make, as a typical function of model complexity. So in our case, this has often been a data where we have been fitting a polynomial to a given order. These are the typical examples which we've been looking at. Now, the nice thing also with these examples, and this is just a kind of small digression, is that in general, there are no kind of ethical concerns with the data which we are looking at. When we are fitting a function, there is nothing which we can retrace back to diseases, politics, race, or whatever. There are data sets which are more controversial. And we actually had a data set last year, which we used in many of the exercises. And as an example of a classification problem, which we won't use anymore because it was a data where some people actually, data set where people felt comfortable about it. It was a data set about breast cancer. And there were students who actually had gone through breast cancer surgery. So every time we mentioned it, that these people were reminded about what they've gone through. And then we have data sets like this credit card data set, which can also bring in some ethical questions like, because it lists age, sex, education, occupation of people, and there isn't bias towards a specific feature of the people who don't pay their credit card debt. So this is also kind of data set. As soon as we come into classification problems, then there can often be some ethical questions about it. We are not going to put much emphasis on that in this course. We will more put the emphasis on the methods, but we will bring this up now and then. That was a digression. But in our case, the complexity has often been a polynomial, which we've been fitting. And what we would typically do then is to calculate the mean squared error for the test data, because that's the one which is interesting for us, whether we are making a good prediction or not. And we are making a prediction on data which was not included in the training. And the typical situation which you will see, and which we have discussed again and again, is something like this. So this would be then the optimal set of parameters, theta opt. Now, when we calculate that once, then it may look like this. But then somebody may give us a new data set. And then when we calculate it, we may get a slightly different curve. So which could look something like this. And then next time, if somebody gives us a new data set, we could get something like this. So the whole idea with these resampling methods is that we would like to narrow down the standard deviation between the different calculations of the test error, or the quantity which we are going to use as a way to assess the quality of the model. So what we would like then is to give people who are going to use our model something like a good estimate, which now could be this line, that one. That would be the mean value of all the samples which we have looked at. And then there may be some difference here between the worst case and the best case, or the middle average. And this is something which we would call the standard deviation, STD, which is the square root of the variance. So typically you would evaluate these mean values, and then you would take and calculate the variance, and you would like to have this variance as small as possible. So one of the things which we saw last time when we looked at the bootstrap was to demonstrate the central limit theorem using the bootstrap as a method, where we simply set up a Gaussian distribution with 10,000 points. Instead of repeating that one another 10,000 times, so we had 100,000 data points, we simply used the bootstrap on the same data set by reshuffling the data points. Now you can show mathematically that the bootstrap method converges towards the correct result. And in this case, it converges towards a Gaussian distribution, but with a smaller standard deviation. So what you want to do then is to provide, without too many efforts, an estimate of the mean square error as an average over many resamples. And that would be the typical model which you then would present. And when you find that the best parameters which optimize the data is here, then you would present the model with these parameters. And then you would present the line which you have here as your best mean squared error. So these resampling techniques are, in general, since you cannot regenerate the data set again and again, as a kind of cheap way of generating new data sets. And we are going to just quickly remind ourselves about the bootstrap method. And then we are going to look at the bias variance trade-off again. And then we move to the cross-validation method, which is also pretty intuitive and simple to implement. So let's just go back to the Jupyter notebook. And before we move on to these methods here, so typically the resampling methods, you can think of the simulations as computer experiments. The results can be analyzed with the same statistical tools as you would use when you analyze experimental data. As in all experiments, you're looking for expectation values and an estimate on how accurate they are. And you're looking for sources of errors. And the two typical sources of errors which we have are statistical ones and systematic. Now, statistical ones are those which we can deal with as statistical analysis, and that's what we are doing. Systematic ones deal with fundamental assumptions about your system. So if you use a fundamental assumption that the system is governed by Newton's law, gravitational law, that is your fundamental assumption about the system. And then when you use this law to interpret experiment, the observations may deviate from experiment. And that brings in what you might call a systematic error, which can be very difficult to quantify because that depends on your model. So statistical errors are things which we can deal with, whereas the systematic one or systemical ones, they're often much more difficult. So we will mainly deal with statistical errors. And that's where resampling methods come in. And as I said, the prediction error, or simply the test error, this is the one which we want to optimize as best as possible. So we have a fixed training set, and the test error is the mean squared error arising from the data for testing. And then you can also discuss the training error, which is the average loss or over the training data. But often we end up just looking at the test error. And you know that from experience now with the different exercises, is that when you increase the complexity of the model, you can train to a pretty good reproduction of the data. But then your model may fail when you apply it to data which was not included in the training. So the bootstrap method, I'm going to quickly remind you of that one and also the bias variance trade-off. But before we do that, let's just break the monotony a little bit and take a look at some of these questions here. So if you look at this code and go to menti.com, so this is just a free question. Why do we resample? So I gave you a quick overview of that. So I just wanted to see what is your opinion on resampling here. So we just take some few minutes and discuss that. So this is just free text. And then I have some multi-choice questions as well. Yeah, that's a good point. Yeah. Yeah. Central limit theorem is very important. If we're assuming that these are independent variables, then we know that in the limit of more and more data, we should approach what is a Gaussian distribution for the different events. Standard deviation. Yeah. Yeah. Exactly. And also not to be able to create a new data set is extremely important. Now, in project one here, the data set which we have is something which we can generate again and again and again. And you've probably seen that. I mean, to generate 1,000 data points or 10,000 data points is something you can do quickly. So in a certain sense, for the examples which we have in project one, doing this cross-validation or bootstrapping, sometimes you may ask yourself, what's the point? The point is more pedagogical. It's just to get you used to that way of thinking, because normally you cannot change the data set you have. So these are excellent questions, excellent answers. So actually more answers, very good. So let's see here. Okay, that was the previous one. Is it okay if we just move to the next? And then we are going to look at this one. What does the bias represent in the bias variance trade-off? Excellent. Perfect. So we are going to repeat some of these things, but it's actually the first question. So it's the spread of the model mean from the target data which we are looking at. And I'm just going to bring back the equation. So the standard interpretation is the one which the majority of you actually have clicked on. Okay, if we move on. So I have another one here. If you look at the bias variance trade-off and you look at the results here, yeah, that seems to be the great majority here. There is no doubt. Excellent. So low bias and low variance is normally what we want. Perfect. This is really good. Thanks, people. Thanks, folks. So I think I have a last one here. This is just free text. But we are coming back to that. If you don't want to answer it, I mean, no problem. But feel free to see or write down what you think the low variance. Yeah. Yeah, exactly. Excellent. These are very good answers. Yeah, you could also have, that point is actually a very good point, the last one. It could mean that the bias is high or that the model complexity is low. That's also something you will see that quite often actually in the calculations. And we are going to look at some examples just to remind ourselves about this. So let me just scroll down and see here, small spread. Yeah, good. These are good answers. Thanks to everybody. So let's go back to the, is it okay if I go back to the Jupyter Notebook? So if we look at the answers, so typically here, low bias and low variance is the ideal. When we look back at this one, the bias represents the spread of the model mean from the target data. And also these are very good answers to the question. Okay. So let's just quickly remind ourselves of this bias variance trade-off. So in the exercises, which you will also be able to reuse in the project, and when you write the theory section, the correct answer is actually the one which you see here. But then in order to do actual calculations, what we end up doing is to replace this F function, which you see here, with simply the target data. And I said that note that in order to derive these equations, we assume you can replace the unknown function F with the target output data. And this is what is done in all practical calculations and evaluations of the bias variance trade-off. Now, a quick reminder of what we did last time was to run an example where we fitted a polynomial of degree 14. We used the resampling with a bootstrap method, and we had a function which we use from scikit-learn, which is called resample. So every time we do a bootstrap step, we actually generate new data points by reshuffling the original one, which is set up here outside the loop. So this is the X data, and so this is just the splitting which we make. And then for a given data set here, we make a model fit, and you see now that the test data is always kept the same, so that is just unchanged. So that's the data which we are looking at. And the X-train data splitting is done outside. And here, in the setup of the polynomial features, what we are doing now is simply we are taking this X-train data set here, and we use that one according to a given polynomial degree. Then the test data is always kept as it is. There is no change of that one, because that's something which you can think of keeping in a safe, and then you do the training with different models. But the test data stays the same all the time. And in this particular case, when we then did the bootstrap resampling, what we got is something like this. And this is a typical case which you will see in many textbooks. But keep in mind that what I did was to tune the number of points and the polynomial degree so that I could get this kind of dip where you have a minimum in model complexity for the mean squared error. And if I were to change this, as we saw last time, if instead of 40 points, I did 400, I would get a flat curve for both the bias and the variance. And you see now in this case here that you can have a very low variance when the bias is high. And that is a model complexity which is low. But when you typically see the model variance increasing, that's a clear flag of you hitting a region where you are entering a domain of overfitting. So let's look at another example. But before that, I'm just going to say something about the bias variance trade-off. So it summarizes a fundamental tension in machine learning, in particular in supervised learning, between the complexity of a model and the amount of training data which is needed to train it. And since data is often limited, in practice it is often useful to use a less complex model with a higher bias. That is a model whose asymptotic performance is worse than another model because it's easier to train and less sensitive to sampling noise arising from having a finite-sized training data set, smaller variance. The above, what we have seen, shows that in order to minimize the expected test error, we need to select a statistical learning method that simultaneously achieves low variance and low bias. So what do we mean by the variance and the bias of a statistical model? The variance refers to the amount by which our model would change if we estimated it using a different training set. And since the training data set are used to fit the statistical learning method, different training data sets will result in a different estimate. And you saw that when we changed from 40 to 400 points. But ideally, the estimate for a model should not vary too much between training sets. However, if a method has a high variance, then small changes in the training data can result in large changes in the model, so which in general means overfitting. So let's look at another example here and go carefully through that one. So this is a simple data set where we are setting up a cosine function. And then we are going to have 30 data samples, and we're going to fit a first order polynomial, a fourth order polynomial, and a 15th order polynomial. So these are the polynomials we want to fit to this function here. And then I'm going now to make a fit and plug in the polynomial features. So I'm running a loop over the degrees here, which is 1, 4, and 15. And then I do a standard linear regression. I perform the plots. And then let's see what happens when we run this model here. So what you would see then is the following. So you see now that when you have a degree of polynomial 1, we have a pretty small mean squared error. It's actually pretty small. These points which you see here are the samples which we are trying to reproduce. The true function is this one. And then this is what the model gives us. And when you look at the model here, this is going to be a model with, when you take the average value of the data, they will roughly not be that far away. So this will be a case when we train a model, there's little variation in the model, and then we get a variance, which is going to be small, but the bias could be larger because you see you have a big spread between the different points and what the model would give you. When you now go to a degree 4, then you see that the mean squared error is getting smaller, and then the model is actually getting pretty close. And this would be a case where you would have low variance and a low bias. Then, when you go to a polynomial of degree 15, now in this specific case, what you see is that you have a model which is trying to go through the data points, which you have. However, the function you're setting up varies widely. So that means that this is going to be a case where for each data point which you see here, you will get a pretty large variance. And you can see that the variance has to be large because this function, just inspecting by the eye, fluctuates a lot. So one thing which you will often see when you train to perfection, you make a more and more complex model, is that you can force the data points to actually go through, or the data points of your model to go through the data points. You can simply do that. But then there can be large fluctuations in the way the function looks like outside where it has been fitted. So what you're seeing here is that the model is actually going through the data points which were included in the fit. Does that make sense? But the blue line, which you see here, that is your prediction after training. So ideally, you would like your prediction to look like this. Now, you have a model now which goes through the data points. You have forced it to go through the data points. But when you then make a prediction, which is the blue line, you have something which fluctuates widely. And this is a standard situation you're entering when you're overfitting. So you can fit very well the data points in the training, which are the dots here. These are your training points. But then your prediction you're making fails miserably outside the fitted points. Because in this particular case, when you look at this curve here, this one, you would actually be close to the true function. That's where you would like to be. So these are the points which were used in the training. But then you see here that you deviate a lot from the true model. And at the same time, you have, if you were to calculate the mean value here and look at the variance of this, you would have a big scatter, which also means a big variance. Does that make sense? So the points which you see, they are just the model points which plugged in here. So clearly, if I bring in, let's say, instead of 30, if I do 100 here, then you will see a different picture. Then you see something like that. So I added now 100 points, which are the points I want to reproduce in this specific case. And then you see now that when you have a degree 4 polynomial, you're still doing pretty well. Whereas with degree 15, you're actually getting a mean squared error, which is pretty large, which again means that you are in a way overfitting again. Okay, so what we are going to do now is to discuss the next method. So when we do a bootstrap, typically we do a bootstrap over the whole data set, and we do it many times. Now the question now is, can we get away with something which requires less CPU cycles? And in essence, this is where cross-validation seems to be a compromise between a good quality of the results and less CPU cycles. And the method is extremely simple. So let's just write it down on the whiteboard. So you will also see that many of these methods, they were proposed simply as a kind of ad hoc method, like the bootstrap was. And then later people came up with mathematical justifications. So the bootstrap method, when Ephraim proposed it, it was just a variant of another popular resampling method, which is called the jackknife. And later they came up with mathematical proofs, which shows that it obeys the central limit theorem. Now, if you look at cross-validation and what we need to implement, let's now just switch over to the whiteboard again and take a look at that. So the cross-validation here. That's an equally simple method for resampling. So one of the central variables is something which is called k-folds, or the number of folds. So let's just write it down here. This is a parameter. And typically, this parameter is something you would have to play around with. And you will do that in actually project 1 and in all further projects. And from practitioner's experience, accumulated experience, typically this k-fold is a number between 5 and 20. If the results don't change when you increase that number, then you would say, okay, now my cross-validation operation seems to yield results which, for the mean squared error, for instance, which do not change much. So let's take a look at what it means. So suppose you take k-fold equal to 5. This means that when you look at your data set, and let's call this for set I equal to 1. Now you would split your data set. So first you do the standard reshuffling. You split it into train and test. And now what you would do is simply to split the data so that the data set which we have here, this one, the red one, this is our test data. So this fraction of data points, which means 20% of the data here, is just set aside for testing. So that means it's not included in the training here. And then the rest here, which I'm going to mark with green, these are the train data. So I'm going to train a model with that data. Now, what I'm going to calculate now is a mean squared error for this model. And I'm going to call this for model 1. So you train, and then you apply to the test error. And this is the mean squared error for test. So that's the first experiment. And now you see the pattern. The next experiment is actually to change which one of these boxes is used for testing and which one is used for training. So what I do next then is to have a new one, which I call for I equal 2 here. And that could be, so if we keep the same coloring. So our training data could, which is the green here, could be this one. And then our test data is this one. So this is our test. And this gives us a model now, which has a mean squared error test, which we just label as number 2 here. Next, we obviously continue here. We have I equal to 3, and this goes all the way down to I equal to 5. And then I split it like this, and now we bring back the colors. So now this time I could have this one and these ones as training data. And this one will be the test case. And it's pretty obvious now the way this continues. So I'm going to skip number 4. And then I'm just going to set up the 5 new boxes here. So this will be the training data. And then the first box is the one which we leave for test. So that means that for this box here, we would have a mean squared error test. We'll label 3. And then there's going to be a mean squared error test with label 4. And finally, a mean squared error test, 5 here. That means that the final mean squared error is simply going to be the average of all these mean squared errors. So this leads to a total mean squared error test, which is simply the sum of a 1 to 5. And then we have a B equal 1 up to 5. And then I have this MSE test. So let's put a bar on top of it to indicate that this is the average. And then we will simply have the sum over all the mean squared errors from these different experiments. Now, there is one variant of this, which is called LOCV, leave one out cross-validation. That means that we actually have to do this if you have n data points, then you have only one data points for training. And then you have the remaining n minus 1 data points for training, and only 1 for testing. And then you do this n times. So you would simply reshuffle all the data points. This is called leave one out cross-validation. So that means that your training data, which we, in this case here, assume that we have 20% here, you could now think of you having only one data point, and that leads to what is called leave one out cross-validation. So that means that only one in data in test set. No, I don't. Yeah. It's an additional O, 2 O's. Yeah. That's right. 2 O's. Leave one out. So let me just correct that one. I was a little bit fast here. LOCV, like that. Thanks. Leave one out, cross-validation. But that becomes pretty heavy computationally, because then you have to run through this n times, which is your data set. So normally the kind of compromise you would do in a numerical experiment is to use this k-fold as an experimental parameter. And then you simply see when the mean squared error stabilizes. Now, to implement this, there are some code examples in the lecture notes where I show how you can use the parts of the options and then write your own code, or alternatively, just use what scikit-learn provides you with. So let's just take a look at that before we move on. So the method itself is actually a method which converges towards a mean squared error for the test data. That does not need to be the true mean squared test error. But let's go back to the Jupyter Notebook and take a look at how we can program that. So let's just bring it up here. And you will find examples here. So this is an example where I just took a plain simple data set. And now I'm going to use a polynomial, which is a second order polynomial. So let's just make a fit with a model which is a second order polynomial. And then I'm going to use ridge regression. So I have these parameters, lambda, which I put to 500. And it goes from minus 10 to the minus 3 to 10 to the 5. And here I say I want to have 5 folds. Now, what this function here is doing is actually setting up how you split the data. So it returns the indices where you can pick up the different training data and test data. And you could then, when you run, so we run over the lambda values because this is ridge regression. And then we have the training points here, which we are setting up. So we find X train and Y train. So we have found these indices, which are actually given by this function here, which now does 5 folds, splits it in 5 blocks. And then I could do my training. I can do my fitting here. And then I calculate the scores, which is just now the mean squared error here, which you can see here. So this is the Y prediction minus Y test. And then it's squared and divided by the size of the data which we want. Alternatively, I can now use the cross-validation functionality of scikit-learn. And in this particular case, what you can simply transfer is actually the value of the method, which is ridge. I give X and Y, and then I want the mean squared error. I have now cross-validation with a number of folds, and then I do my cross-val score. And this returns the error, the estimated error, which is now the mean value. And then when we plot it, we are going to get something which is not going to be too surprising, which looks like this. And we expected then, because we have a second order polynomial, which we are fitting pretty well. And we see now that the error is pretty small. And then when the lambda values increases, we start to shrink some of the parameters which we have. And at the end, we are just approaching the mean squared error with the target values only squared. Now, what you could do now, and this goes a little bit back to what we are doing in project 1. So suppose now I didn't know anything about the function, and I say I want to make this to be a sixth order polynomial. So I'm going to fit a sixth order polynomial to something which is actually a second order polynomial. Now, there is an interesting thing, and this is a little bit linked with project 1 here and what you might expect. So this is my cross-validation score for the mean squared error when I now use a sixth order polynomial. So if I didn't know anything about the function I'm fitting, so I'm just guessing on a sixth order polynomial. Now it does a fit where you can see that the mean squared error here has a minimum. So when you are now picking the best parameters for your model, for ridge regression, what you would say then is that 10 to the power of 1 something gives me the best mean squared error. In this specific case, I have a polynomial of degree 6, which I'm fitting to a polynomial of degree 2. But when you're running both cross-validation or bootstrap, you would have seen something similar with bootstrap, and you have ridge regression, this is something which may happen. And that may, deceive you to believe that the best way to fit this function, because in the previous case, we had a mean squared error of 2 roughly, but now we're getting a smaller mean squared error, and that this polynomial of degree 6 is a better fit to the data than a polynomial of degree 2. So this is something which you need to play around with a little bit to gain insights about the kind of results you're getting. So here, we got a better mean squared error, but we are fitting a second order polynomial with a sixth order polynomial. So these are things which can happen when you use these hyperparameters to tune a function. Does that sound confusing? Now just be aware of that sometime if you get a better mean squared error than another method, it may not be that you're fitting the correct model or the best model. Okay? Does that sound reasonable? Because we don't know what's the best model. I hope this doesn't add too much confusion, but keep in mind that when you're optimizing with these additional hyperparameters, you're optimizing a different function than just the mean squared error. And then you go back and you calculate the mean squared error. And in this particular case, we actually get a result which looks better with a hyperparameter lambda, but we are fitting a sixth order polynomial or second order polynomial, which may not be the best fit. And clearly, these results, before we take a break, these results will definitely change if I have more samples. So if I run this with 1,000 samples, then the results will typically change, and you would get something like that. So if you try to fit a sixth order polynomial with just 100 points, you found that ridge regression gave a better result than the mean squared error. But then when you increase the training set, the size of it, you're getting a better result, which actually matches with what you might think would be the decent result. Okay? So at the end, it's you who has to make the decision of what is the best model with the parameters you're tuning. I went a little bit over time. It was deliberate, actually, because I wanted to finish this part. So to implement these methods is actually very easy. And for project one, I typically recommend to use the functionality of scikit-learn. That gives the least. So in the Jupyter Notebook, what we will also find are some other examples. And in this specific case, we have a data set, and you don't need to look so much at the data set. This is actually the data on the energy of protons and neutrons in a so-called neutron star. So this is a simulation which has been run, a theoretical simulation, where every point in the simulation took several CPU hours. And there are some 100 data points. Now, in this case, we are trying to fit this to a polynomial of a certain degree. And if you now do cross-validation, so the example which you see here, now we are trying to fit a polynomial of degree 30, and we are simply going to do plain ordinary least squares. But we are going to do that with cross-validation. And in the example here, I start with 5 folds, as you can see here. This is k equal to 5. And then I call the splitting of the data sets. I run over the polynomial degree, so I'm fitting up to polynomial degree of 30. And I am now setting up a function, which is a function of density to the power of the degree divided by 3. So this is an assumption about the density dependence. Now, if I run this with k-fold 5, you will see something like this. And in this particular case, you would then say that, okay, for a polynomial degree of 5, this is roughly where I should find the best possible model in this specific case. Now, one of the things you need to do when you're using the k-fold or cross-validation is to play a little bit around with the number of folds. So if the results stabilize, if you look at this one here, you will see now that it roughly has the same minimum. So with a k-fold between 5 and 10, you're getting a typical minimum for the prediction which you're making, which says now that the polynomial of degree 5 is the one which seems to give the best reproduction of the data. So that's a typical example you would then face when somebody gives you a data set, where you typically cannot just generate new data continuously. So that's just a typical example of what you might expect. So keep this in mind when you're playing around with these different parameters. When you do the cross-validation, you need also to test whether the data which you are testing show a kind of convergence for the mean squared error, or the kind of test function which you're looking at. Now, what I want to do now, after this discussion of cross-validation, is to move on to our first classification algorithm, and that's called logistic regression. And it has much of the same spirit as we did for linear regression, but there is a notable difference. So let's discuss that notable difference here. So I'm going to go back to the whiteboard, and we are going to use this case with logistic regression. So not only to introduce classification problems, but many of the functions which we need to deal with when we are going to deal with neural networks. So that's why I say this functions as a stepping stone towards neural networks, because we are going to introduce a so-called activation function, which is going to play a central role in the design of a neural network. So you can think of this as a preliminary step, but at the same time, it's a widely used way to classify data. So let's switch over to our next topic, logistic regression. So let's just write that. So this is our first classification case or classification algorithm. And I'm going to derive some of the basic equations. So let's take a closer look at what we have done in linear regression, because we made an assumption about the data where the variable y of I, the output or target value, is a function of a continuous function, which we in principle don't know, plus some epsilon of I. Now, this epsilon of I is assumed to be given by some kind of stochastic noise, which is normal distributed, Gaussian with mean value 0, and standard deviations sigma. The basic assumption we made about the data is that these x of i's could take values from -infinity to +infinity, or, so let's just put that in brackets, there could be a minimum value xa and a maximum value xb. So it's defined for a domain, and this f of x, the assumption we made is that f of x is a continuous function. What we also assumed is that the y of i's, they are also variables which can take values from -infinity to +infinity, but normally we would have them constrained in a domain from y of a to y of b. But the assumption we have made about the data is that these are continuous variables, both the x's and the y's, okay? And then we can fit a continuous function like with a polynomial fit. So what we did then was simply to assume that our y of i's can then be described by the sum over some polynomial parameters. And I just leave this j unspecified. We have the elements of the design matrix. This is multiplied with theta j plus some epsilon of I. And this defines our model, y of I, which again is our approximation. So we should put an approximation sign here, because y of I is an approximation to x of I here. Okay, that's a basic assumption which we have made. Now, suppose that we are fitting a first order polynomial. So let's do that. And we are fitting this with some y of I, which we are now approximated with some theta 0 plus some theta 1 times some x of I plus some noise epsilon of I. So let's now ask ourselves, what if these y of i's are given by discrete values? As an example, we could now assume that there are only two possible y's. So we could now assume that y of I can either take the value 0 or 1, right? So this is normally called a binary case. So let's now look at a typical data set, which we now could encounter when we plot y as a function of x, okay? So there is nothing which hinders us to actually try to fit a straight line to reproduce either zeros and ones. So let's now look at a data set, just a data set which I made up. So suppose now that we have from 0 to 1 here. So this is the y, these are the y values, and then we have the x's. And I'm just going to drop a 0.5 here. This is y equal to 0.5. And now I'm looking at my observations. So I have an observation here. I have an observation here. I have one here, and then there's one here. I may have another observation. So let's just draw a line here. So I could have an observation here, but then I'm having most observations here. Now, I could fit a line to this. And this line would now be a line which perhaps could, let's say, look like this. So I could make a fit here which goes something like that. And then I could say that for the values below a certain value here, I'm getting zeros, but I would obviously miss that one. The other thing is that this line here, that goes from y minus infinity to y plus infinity. So suppose now you fit a line to this data. There's nothing which hinders you doing that. Sometimes this line may separate nicely two sets of data. So let me just give you another example. So this example is perhaps not the best one. I could have another data set which looks like this. So I have a variable x1 and I have a variable x2 here. So this could, for instance, be you recording on x1 how many hours you slept, and on x2 how many hours you studied for a given course. And then you could think now of the circles here representing a grade which is below the average grade. That could look something like this. So these are the circles. So now we take a group of people who attend a course, and then we simply correlate the number of hours you slept, x1, with the number of hours you studied. And then somewhere here, there is a grade which is then above the average. So if you have these kind of nice separations, you could obviously fit a straight line here, which goes like that. And you would say then that if the value is below this line, then you get a grade which is below average. If it's above this line, you get a grade which is above average. Now, in this particular case, you have something which separates well, but that's not the normal situation. Normally, these points are often mixed, and it's not possible to fit a straight line. The other thing, if we now go back to the figure which we have here, in this case, we actually have only y values, which are 0 and 1. And fitting a straight line to a problem like this could, if we are lucky, we could separate the values. But in general, this is not the case. And in addition, this is a line which goes from minus infinity to plus infinity. So what we would like to do then is to fit another function. And this function could be a probability distribution. And that's actually what we are going to do. So suppose now that you fit another function which looks like, suppose it looks like this. And then it rises like this, and then goes through the points here. Now we have some outliers which we are not able to fit. So these are the two green points, one below and one above, which would not be included by that function. And what we could say then, if you now look at this specific function we have plotted, is that the data for this function here, and let's call this function for p of x. So what we could say now, if p of x is less or equal 0.5, then y, we put an x of I here, y of I is equal to 0. Else, if p of x of I is larger than 0.5, then we say that y of I is equal to 1. So by training that function, we can use that function to put out a threshold value and say that if the threshold is below a certain value, it has to output 1. If it's below, it has to output 0, and if it's above, we output 1. So then we make a model. So this kind of situation is something you will encounter in many, many cases, this kind of S-shaped functions. So what we're going to do now is simply to make a new ansatz for that function. So we are simply now going to say that this y of I, which we previously assumed was given by a continuous function, which gave us values from plus infinity to minus infinity, now it's being replaced by a probability. So we replace it by y of I, given by some p of x of I, plus some epsilon of I. And this p of I is going to play the role of a probability. It's still a continuous function, but it now takes values in a specific domain only. So this function, which we are setting up, takes values between 0 and 1. You can always change it to another domain, but it's well defined between a specific set of values. We are also going to assume now, so we are going to assume that this can be interpreted as a, and now I'm going to sneak it in here, a probability. Probability. What does that mean? Now it means that the function has to obey some specific properties, and these properties are properties like the following. So we can normalize it. So x integrated over a specific domain of this d of x is normalized to 1. We can have a discrete probability. So if it's discrete, we would have a sum of I in a domain of events which this probability is defined for, and that should also sum to 1. We assume now that this function is defined when we have x between 0 and 1. So there should be a 1 here. Then what we have is that p of 1 is defined to be equal to 1. P of x of I is less or equal to P of x of j if x of I is smaller or equal x of j. So these are some of the properties which we require for a probability. And one of the functions which is the simplest one to use, and you may have encountered this many times. So the first example, which gives us a continuous function, is the so-called sigmoid function, or just the S-shaped function. So this is a function which has these properties, and it also gives us values between 0 and 1, so that we could actually fit a sigmoid function to play the role of this specific function here. So let's look at the mathematical form of the sigmoid function. So this function, p of x, is something which then is defined in terms of an e, and we have a theta of x. So theta is now the parameter which we want to optimize, plus e times some theta of x. This function can be normalized. If I now want y to be equal to 1, then this we could now define a probability function, which is given by e of some theta times x plus 1 plus e of some theta times x. And if I take y equal to 0, then I know that this must have a probability of 1 minus p of x. Because if I define y equal to 1 to be equal to this function with these parameters theta, then y equals 0 because I have only two options, either 0 or 1. Then that must have a probability which is 1 minus p of x. And then you will see that if I sum over the two cases which I have of p of x of I, for these two cases, that sums to p of x of I minus 1 minus p of x. That one. Let me just write it like p here. So if I take the case with y equal to 1, then I have p. And then if I take y equal to 0, it's 1 minus p, so that the probabilities sum up to 1. Now you can show that this function here because this particular case is 1 divided by 1 plus e times beta of x. So if you sum these two functions, you see immediately that what you're getting then is actually 1. So this plays the same role. It can play the same role as a probability. You can normalize it, and you will also find that when the specific function has the value, when x has 1, it should then give us the value which we want then for the top value. Now we can make a graphical representation of this. And this is the way we are going to look at the problem when we come to neural networks. So you can now think of this, if x is a scalar, this is now being input to a specific function. And this function is now going to be just labeled in a generic way. So it takes in an x value, it has a parameter theta. So in our specific case, this is going to be this sigmoid function if we want to. We will often write it simply like a p of I, like this. So you're inputting the variables to a specific function. Now this function then gives an output. And this output could now be a threshold. So where you now set in, we have, let me just put in some more colors here. So we have 0 and 1. And the function now has a threshold that if it is less than a half, it produces 0. And if it's above a half, it produces 1. So this gives us now an output. So I'm just going to continue along this line. So this gives an output, which is just y of I tilde, which in our case is given by a discrete set of variables. Then we are going to feed this in to a cost function. This is a function of now the parameters theta. And in here, we are going to feed the target values, the outputs which we want to fit. And keep in mind now that in this case, which we have specialized to, which is a binary case, y of I tilde takes values of 0 and 1. And similarly with y of I, it takes values 0 and 1. So what we are doing now is to set up a model where we now feed in the data into a specific function. And this specific function is now given by a specific probability here. We can have some additional noise if we want to. Depending on the value which we produce, we have then a threshold where we output either 0 or 1. So what we're going to do now is to train such a function. And we need to find a specific way by which we can define this cost function. Okay, we haven't said anything about the cost function. And in this particular case, the mean squared error is less useful for that case which we're going to look at now. Now, keep in mind as well that in general, our design matrix, X, is now going to be a column matrix of the different features. So I'm just setting X00, X01, and then we have P features. So we have P minus 1 here. And then we have X10, X20, and then down to Xn minus 1. These are the data points which we have, down to X. This should be N minus 1, 1. And this goes all the way up to Xn minus 1 of P minus 1. So these are the data points which you now want to fit here. Let's take a look at how we can set this up when we come to this more general case. So when we have this more general case, we are going to have this function sigma, which I write just as a sigma now. It's going to produce an output according to the threshold which we have put in here. So there's this function here, we are fitting 0 and 1. Now it receives lots of inputs. So we would have x of I0, x of I1, down all the way to x of I p minus 1. And they all feed in here. So instead of having just one variable, we are now feeding in many variables. So just keep in mind that the simplistic case is actually this one, where we just feed in one variable. But in general, we are going to deal with a design matrix, and that means that we're going to feed in a whole set of variables here. And this is then going to produce an output. So these variables will produce just one output. And in our case, these are going to produce y tilde here. And that would be a y tilde of I here. So this is just a kind of small reminder. And what we are going to do now is to make a simple model. So the simplest possible one we can make now is a case where we have an intercept line and just one column with the parameter θ1. So we're going to make an ansatz for this P of x of I, which is given by an E of θ0 plus a θ1 and an x of I, divided by 1 plus E of θ0 plus θ1 of x of I. So that's the function which we are going to fit by trying to find and define a cost function here. So how do we define a cost function? So let's now look at a set of events which we assign a domain. So we have a set of events here where we have an x0, we have a y0, the output, we have an x1, y1, and this goes all the way up to the final data point, x minus 1 and yn minus 1, like that. Now we are going to make an ansatz for the probability. So we have made an ansatz for the single events. So this gives me my y value. So remember now that y of I, the individual one, is p of x of I plus epsilon of I. And we are going to write that as a p of I plus some noise epsilon of I. So this is the ansatz we are making now about the data. And we are going to take this function here, because that's going to give us a simple function to optimize. Well, simple and simple, it's a little bit more complicated than what you've seen before, okay? So that means that if I look at these probabilities now, since I have a binary output, what I could say now is that the probability for the whole domain with respect to these parameters theta, with a given set of parameters theta, I'm defining this as my cost function. This is the function I want to optimize. So I'm assuming now that all these events are statistically independent of each other. And I can now write out this probability distribution for the whole domain as a product of the individual ones. And now I'm going to use the standard binomial formula. So which says that I can go from y equals 0 up to n minus 1. And I have p of I to the power of y of I multiplied with 1 minus p of I to the power of 1 minus y of I. And now you see that if y of I is equal to 1, then clearly the probability is equal to p of I. If y of I is equal to 0, then I have p to the power of 0, which is 1. Then what I get is 1 minus p of I. Okay? Have you encountered that type of distribution before in statistics courses? Because I have a binary case. So that means I am making a model now where I'm simply looking at all the possibilities which I have, which are 0 and 1. So the probability for 1 is simply given by this case, because then this one is just 0 to the power of 1. 0 to the power of 0, or 1 minus p of I to the power of 0, which gives us 1. And then I have p of I, in case y of I is 0, because all these outputs which I have are either 0 or 1. And then I know that the probability for 1 is given by this one, and for 0 is given by this one. So that's a way of setting up an ansatz for the total global probability here. Does that make sense? Okay. Now, if you look at this expression here, this is something when I now want to calculate the derivative of this P of D of theta, and this is actually what I want. I want this gradient here for a given parameter J, and I want to drive them all to 0, as we did before. So what I want to do now is to maximize my probability. It doesn't make sense to minimize a probability. I want to have a probability function which gives me the maximal output. So if I give a minimal output, the probability is 0. So I don't want to have a function like that. So I can maximize, or I can minimize if you want to do that. But then we have to be a little bit careful. And also, if you look at the product which we have here, this is going to give us some more complicated expressions for the derivatives. Now, if you think back to what we did last week, when we derived the ordinary least squares equation from a probabilistic point of view, what kind of function would you propose which makes life easier? If you look at this as a product now. So you can optimize that one, either maximization or minimization, or you can use another mathematical function which makes life easier, which also gives either convex or a concave here. We take the log of that one. So instead of optimizing that function, which we can do, but it's going to give us more complicated expressions, we can now define a new cost function, so which I'm going to define as a c theta, and now I'm going to put a minus in front of it, because the minus one is going to give me a minimization problem. So what I'm going to find then is that theta, the optimal value, is going to be given by the minimization with respect to all the theta values, which we have at hand, of minus log of this function P of D of theta, like that one. So what I'm going to do now is simply to take the log of the function we had on the previous slide. So on the previous slide, what we had then is that this probability, just to remind you quickly about that one, this is simply the product of I equals 0 to n minus 1 of P of I to the power of Y of I, multiply 1 minus P of I to the power of 1 minus Y of I. So when you now take the log of this product, you're simply going to get the sum over all these individual contributions. So you will have a log of P of I to the power of Y of I. There will be a log of 1 minus pi of I, etc. So if you now look at this function here, the cost function, it means that your cost function is going to look like C of theta, and that's going to be a sum over I equals 0 to n minus 1. And then the first term is going to be Y of I of log P of I. And then I'm going to get a plus 1 minus Y of I of log of 1 minus P of I. So this is the function which I want to calculate the derivatives of. And if I now plug in the sigmoid function, if I now look at log of e to theta 0, this is a 0 plus theta 1 times x of I divided by 1 plus e to the theta 0 plus theta 1 times x of I. If I look at this function here, we know that this is simply nothing but theta 0 plus theta 1 times x of I. That's the first term, this one. And then I get minus, and then I have log of 1 plus e of theta 0 plus theta 1 times x of I. Then I'm going to use that one, this expression which you see here, I'm going to plug that one back into here and here. So if I do these manipulations, then I'm going to get a function which is a little bit simpler to calculate the derivatives of. And that's why we use the log when we have the product of all these probabilities. Because we can then choose to have minus log, which is a convex function, or we can have plus log, which is a concave function. So if I now plug this in, this expression here, into what we have here, what I get at the end is the following. So I get that C of theta is now going to be given by this sum, I equals 0 to n minus 1. I have y of I, and then I have theta 0 plus theta 1, x of I, minus, and then I have log of 1 plus e of theta 0 plus theta 1 of x of I. And then we put a bracket parenthesis here and a bracket here. And what we want now is dc d theta 0 equal to 0 and dc d theta 1 equal to 0. And these are the two derivatives which we want to set up. And what you will see then when we set up these derivatives is the following. So let me just set it up. So the first one, dc d theta 0, is simply going to be equal to minus I equals 0, n minus 1, and then I have y of I minus p of I. And p of I depends on the parameter theta. So now we are going to get a set of equations because our approximation is not a linear function anymore. It's actually a probability which depends on the parameters through the exponential function. And what we will get now is something which is not a simple analytical expression for the parameters theta. And we have to use gradient descent to solve the equations. So if we go to the next one, what we get then is that dc of d theta 1 equal to 0 is then simply equal to minus, and I'm just going to end pretty soon now by setting up the more general equations. And then we have an x of I of y of I minus p of I. So the general equation, if we have more than just one value, is that this dc of d theta, and now theta is a vector, is actually given by minus x transpose, the design matrix, of y minus the probability. So these are now vectors. And now remember that this depends on theta. So we cannot single out the theta values, because if you now look at the p of an x of I here, it's actually given by e of theta 0 plus theta 1 times x of I divided by 1 plus the same expression here. So we don't longer have a linear dependence. So we've made a model for a probability, and this probability could obviously have been another function. Now, one of the reasons why the sigmoid pops up is that this allows us, through this S-shaped behavior, to fit data like those which I showed. It's easy to calculate. It has simple expression for the derivatives, and this is something which becomes important when we are looking at neural networks. And for a neural network, we are going to actually have so-called activation functions, where this sigmoid function is one of the typical activation functions we will encounter. There is another thing which we can calculate. So we can calculate the second derivative, which is the Hessian matrix. So we will have a d theta which in this case is given by the matrix X times a new matrix W times X, where this matrix here has diagonal elements, only diagonal elements, which are given by P of I of 1 minus P of I. And Wij is equal, when I is different from 0, is equal to 0. So this is a diagonal matrix. So what we have then, when we are setting up Newton's method for this, is that the parameters theta of n plus 1, and this is Newton-Raphson, is going to be given by n minus, and then we have a learning rate, and that is going to be multiplied with this gradient which we see here. And this gradient depends on the previous value of theta. So that gives us dc d theta at theta equal to theta of n. So we have the derivatives. That means that you could now, with the programs you have developed for gradient descent, you could simply replace the gradient you have now for ordinary least squares with a gradient for logistic regression, where you feed in this function, the sigmoid function, or other similar functions which behave like probabilities. So to summarize, what we have done is now, since we have a binary classification case or a classification case with discrete outputs, we have now assumed that the data are not given by a continuous function f, but they're given by a probability distribution. And we use then that probability distribution to define the threshold for the output. So we are going to train a function now, which is a probability distribution, which can give us 0 and 1, or it can give us more values. So we can have a multi-class function. And we will discuss that next week. So I wanted to set up the equations. And next week, we are going to discuss how to implement this. But you see the pattern. When you have a gradient descent code, you can actually plug in many different types of cost functions. And then this gradient descent code will in a way be agnostic to the type of problem you're dealing with. So basic takeaway message, we are now fitting a probability distribution, which we want to produce a binary output or an output which can contain many more classes. So we are not confined to just 0, 1, yes, no, but we can have many other different classes. And this leads to multi-class probabilities, which we will discuss next time. So if you want to use this to classify numbers, handwritten numbers from 0 to 9, you have 10 classes. So then you need to move away from a binary problem to a problem with 10 classes. And each probability tells you the probability of finding 0, 1, 2, 3, 4, etc. So this is the basic philosophy. The calculation of machinery is not that different from what you've seen, but the cost function is more complicated. Okay, we'll take a small break, guys. This is going to come in full force into project number 2. And it's a stepping stone towards neural networks. Okay, have a good afternoon and enjoy your time, and see each other at the lab this week.